Most people in Silicon Valley believe that we just make AI models bigger, potentially smarter, in inverted commas, and faster, they will eventually become intelligent. There's a fundamental problem with that idea. Today's AI systems are incredibly good at predicting the next word, the next set of words in a sentence, but they don't actually understand meaning. And that limitation creates some of the biggest problems businesses are facing when they're trying to implement AI in the real world. I've spent the last decades building AI companies, working with large enterprises, and what I've seen repeatedly is a real challenge with the AI isn't the model. It's the architecture underneath them, the data underneath them, and the foundations. In this video, I'm going to explain to you the AI problem most of Silicon Valley is just not seeing, and why solving it could create one of the biggest opportunities in technology in the next couple of years. I think what you're seeing right now in many spheres of the tech industry, especially in Silicon Valley, is this huge focus just on the language model itself and the belief that the language model will be sort of the be-all, end-all of it. I think we need to take a step back and realize that actually true intelligence is based on three facets: meaning, reasoning, and emotion. And if we take emotion out for a second, it's really meaning and reasoning coming together. And one way to look at this is that meaning is stable. We have collective user history, the things that we've learned, the topics that we've understood. They don't change every morning or every week. And reasoning is actually that ability to move between those sort of stable atomic units. And I think that's really where there's a change in what we're seeing. Everything from world models that Jan LeCun has been talking about and has set up a new company and raised almost $1 billion for. But you're also seeing this entire now movement towards neurosymbolic, where it's really that symbolic referenceable base, and then you're using the language models, or actually a sequence of language model, to find the path or navigate the map versus be the map. And this is really important because it moves away from saying the answer to everything is brute force. A really good example of this, for example, is in software engineering. If you imagine software applications, we use the word feature a lot as an atomic unit, but the language models are just generating lines of code. Even lines of code that in probabilistic terms, 2 million people, 3 million people generated yesterday. And so the point here is that, if the language models were actually using a base of language and meaning, they would say, well, I don't need to generate this again. I don't need to use GPU. I don't need to use this amount of energy. I don't need, sort of that entire modern stack. I should be able to just reuse what was already there before. But that entire dictionary is missing from the roadmap of AI that we're seeing in certain centers around the world, including in Silicon Valley. And then I'd say the final part is it's like the bigger the model, the more intelligent it will become. Kind of yes, kind of no. I think the right way of looking at it is the bigger the model, the bigger the brute force. But also keep in mind, the more paths it can go down. And this is also what's really important with sort of what I've been seeing over the last couple of weeks around context windows. There was a lot of conversation over the last 2 days. Anthropic and Claude have launched the 1 million token context window. And many people were celebrating. The same people that were celebrating were they're saying they're using markdown files to keep memory. And so I'm sort of scratching my head at this point saying, in computer science, that the one thing you learned was you don't keep things in a flat file. The other thing you learned was you don't just have open-ended variables that you just dump everything in hoping that it's going to find the answer. And that really what you're after is carefully nuanced reference points to be able to use to synthesize, to find, derivatives of or to reason around. Versus, here are 50 documents because they can now fit in, or here's a code base because they can now fit in the token window, go guess your way through it. One way to think about language models and why it's really important to figure out the atomization or what the right atomic unit is. It's a little like, for example, building. You've got sand and water that can let you build bricks, and then, sand and water, you could build a building. Or you could use, bricks to build the building. Bricks is just an easier atomic unit. It's built from sand and water, and so much like concepts or ideas are built from tokens, but they're easier to move around. They're a better unit of understanding. You know how many bricks you're going to need to put that wall together. They're easier to also connect and mix around, different types of brick, corner ones. Same thing applies with Lego. You've got a certain number of Lego blocks that exist in everything, and then you've got like finessed ones or specific ones or specialist ones that you need for particular sets or particular things that you might be trying to build. And I think the same thing applies in AI and applies to language models. You can't just be operating at the token level. It's just too small an atomic unit. And then when you make the models bigger, you're also saying, on one hand, I've got more paths to go down, which is why we've also seen in some cases, actually many cases, the smaller models actually outperform the general big models on specific tasks. And I think this is the other piece, right? The reason you have such big models is you're trying to find general model, like a one model that does everything. But as we know, and we've seen this time and time again, a single thing can't do everything brilliant, right? It's a jack of all trades. And what you really potentially want are smaller models that can be sequenced together, that are very good at certain parts of a process. And that's really where you start to get this sort of mixture of model, mixture of agent, mixture of expertise, mixture of experts, structure. And that becomes much more powerful because each model is doing what it's good for and it has less paths to go through. So it's much more accurate. Now you take that and you add it on top of a symbolic infrastructure, like a concept graph. And now you've got something really powerful. You've got a mixture of models that are navigating a map, and the map is stable, right? The map has relationships between the elements on it. And that means navigation becomes a lot more predictable. You can still find new paths, but you're not finding a new path every single time because you couldn't remember the old path. You're losing $33,000 a year to an AI problem nobody's talking about. Here's how to fix it in 12 minutes. You spend hours every week refinding information you already have. Your AI resets almost every session. Your tools store knowledge, but never think with you. This 12-minute research briefing breaks down the architectural reasons why and the neurosymbolic approach that changes everything. You know, one of the most interesting things around how modern day language models are working is we're sort of assuming every problem is being solved the same way. A generalist model versus specialist smaller models is a good example. But another one is that a lot of the times the generalist models are running on GPUs, so they're running on much more expensive chipsets. Whereas they could be running on, say, a language processor like Grok with a Q, and you would get much faster, much better outcome, and actually at a fraction of the cost. And that's the difference between inference and having to sort of do the heavy compute that a GPU would do. And a good example of that is how we talk. Or if I said to you, help me complete my sentence, what do you think the word you're thinking about is say. There were millions of words I could have chosen, but say was the one you inferred and you filled in the gap. And that's exactly how a language processor works. And so running models that can actually run on an LPU means that you're actually getting a far better outcome. And then you take that and you couple it under a symbolic infrastructure underneath. There were many research papers, many articles written in the beginning of 2026 which said the next 2 years is going to be the year of context, and it's $1 trillion industry in itself. But what is context and why is it so important? And the real reason is context is that stable relationship of elements that allow you to really understand the meaning of what you're asking the language model to reason over. And so now if you imagine we take this whole thing together, you use GPUs where you need to use GPUs. For everything else, you use smaller, maybe open source models running on inference. Then you actually are reusing symbols or reusing primitives that are allowing you to fundamentally put these building blocks of knowledge in your own context together. And what you end up having is a system and solution that's far more efficient. A really good example of this, again, is in software. If you took the top 1,000 GitHub repositories and you added up all the lines of code, you'd probably be in the hundreds of millions, tens of millions, if not hundreds of millions of lines of code. And actually, we're doing this study right now. So hopefully in the next week or so, we'll actually have this information for you. If you then said, okay, you know what, I'm going to take the high level abstraction. I'm going to figure out all the features that are in all the 1,000 repositories. How many of these features are actually duplicate features? How many times can we actually assume it's the same feature written a different way, a little like 1 + 1 or ONE plus ONE. And what you start to realize is actually the number of unique features is very small. And if you took that line of code out for every single thing that belonged to one of those reusable or sort of those unique features, what you find is that the tens of millions or the hundreds of millions of lines of code drop by an order of magnitude, maybe even 99%. And actually, you could just reseed those reusable features everywhere. And that starts to give you, in essence, a view of how this new world will change when you start to have symbolic infrastructure, meaning and context. And then on top of that, language models that are navigating and generating and synthesizing and reasoning on top. One of the things to keep in mind is that whenever you generate an answer every single time, you're losing the stability of the outcome. And we've seen this in examples where an airline, for example, put agent powered by a language model with no real guardrail and realized that it was giving incorrect information, incorrect ticketing, incorrect outcomes to the customer, and it cost the customer a lot. Another example was the cases that we saw in the US where certain lawyers were actually using language models to do the writing of briefs or the filing of of court cases, and that actually was hallucinating precedents. And the reason is because, well, it doesn't really know, right? It's just trying to figure out what the next set of words are. And what you want is you actually want to build an AI system that can really leverage the power of language models and generative AI, but also has the stability and deterministic outcome of the classical systems. And why is that important? Well, let's take an example of a call center. A call center might be getting, let's say, 100 million minutes of calls a year, right, into an airline. And if you thought about that, 100 million seems like a really big number. But actually, if we thought about the kind of conversations, changing my seat, changing my flight, booking certain transfers, adding passengers, there's only a finite number of combinations of the things that I'm ringing the airline for. And if I took the amount of minutes to discuss each one of those things and I added them all together, it definitely is not going to be 100 million minutes. It's probably going to be more like 20, 30,000 minutes. And now solving a 20, 30,000 minute problem is infinitely easier. You get much better outcome, much more stable relationships than a 100 million minute problem. And why is that? Well, because even if I took the 20, 30,000 minutes, I could break them into units of conversation. Here are the 5 ways we say hello. Here are the 10 ways we say goodbye. And by the way, when they're talking about changing seat, this is the conversation pattern. When they're talking about making a booking, this is a conversation pattern. And suddenly the whole thing becomes simpler. It becomes much more predictable. And then you use the language models to use the right set of words, the right set of communication that allows the customer company relationship to continue to develop. That's really important because now you actually have a tangible outcome where you've been able to use agentic AI to actually help you in a call center experience without the risk of wrong answers, hallucinated answers, and actually giving incorrect information to the customer. If you're building a company or leading a team and want to understand why most AI tools are still forgetting context, not really understanding context, I put together a research briefing called The AI Memory Gap. It explains the architectural reasons today that AI systems still struggle with understanding and memory, and why the next generation of AI will look very different. If you're interested, you can download the free briefing in the description below.